All right, so today let's talk about relative velocity and acceleration. Our objective for today is to be able to use the frames of reference to describe and calculate relative velocity and acceleration of objects in motion. The essential questions that you all should be able to answer after watching this video and taking notes are: what is a frame of reference and how do we use it in physics? And can velocity change? So after you finish taking notes here, I have left the summary section in this note template blank, so you all can go back and write a 1 to 2 sentence summary trying to answer these essential questions here. All right, so again, we are taking notes in Cornell Notes format. So what I want you to imagine is that on your left-hand side, this left column, these are really just meant to guide you to different parts of your notes. So imagine the left-hand column are the chapters in a book, and the right-hand column includes all of the information that you need in each chapter. Okay, so let's first start with our first idea. What is a frame of reference? So a frame of reference, I'm going to zoom out a little bit, is a certain perspective a scenario is viewed from. Okay, so you all have different perspectives in any scenario that you come across, right? It doesn't have to be a visual scenario. It could be an argument, right? It could be some sort of debate. Everyone should be used to the term what a perspective is. So we're talking about using different perspectives in physics here and different viewpoints to create a frame of reference. So for example, a frame of reference could be, say you're standing on the side of the road and you see this car zooming past you at a really, really fast speed. And you're like, wow, they're moving so fast. And you might say from your point of view, right, you're standing right here on the side of the road, and that car looks like it's moving at like, I don't know, 10 meters per second. So that would be an example of a frame of reference there. In contrast, say that you are in the car. You're in the car and you see another car moving around on the highway. So let's say we are in the car here. Let's zoom out a little bit. So when you are in the car, that car is going to be looking like it's not really moving, right? You are moving kind of at that same rate as the car, but now that ground that the car is moving on is going to look like it's moving really fast. So now all of a sudden it looks like the ground is moving at, I don't know, 10 meters per second this way. So that's what we're kind of getting at with a frame of reference here. So frame of reference is kind of just talking about different viewpoints from the physics perspective and how they can affect what we see. Move these out of the way. All right. So we can use these frames of reference to talk about relative velocity. So our second chapter of our notes that we are getting into today is what is relative velocity. So I'm going to move over, zoom out a little bit so you all can see. All right. So relative velocity, this is another vocabulary term for you all. Relative velocity describes the velocity of an object from a certain frame of reference. So while the object's velocity is not necessarily changing, the object's velocity does depend on your perspective. So let's talk about what I mean by that. So the equation that we will be using for our talking about our frame of reference and relative velocity is VAB equals VA minus VB. And we will be using the same units of measurement for relative velocity that we use for velocity, and that is meters per second. So the distance traveled, your displacement over a certain amount of time, over certain seconds. So let's talk about this equation a little bit more. And I'm going to zoom in here so we can talk about this. So VA, VB, VAB, what does that mean? So let's say that we're taking it back to the car example, and you are looking at, let's let VA be the car. VB is going to be you. So you're looking at this car zooming past you, and you're saying, wow, that car is moving so fast. So I wonder how fast that car is moving compared to your perspective. So you might say that car is moving 10 meters per second. Okay, so say I have, let that equal 10 meters per second. That's how fast the car looks like it is moving to you. So this is what is going to be our VAB. This is our relative velocity according to VB. So our frame of reference is VB. Now, the VA is the actual velocity of the car. So the car might look like it's moving 10 meters per second from your perspective, from your frame of reference, but maybe in reality, it's actually only moving 7 meters per second. Okay, so this is what we're getting at with our frames of reference here. So I'm going to just quickly erase these so y'all can have some nice clean notes. Oops, and I totally chose the wrong tool there. Let me just quickly erase that. So we will say that VAB is the relative velocity. This is the VA is the actual velocity. I'm just going to type the right actual V for short. And this is the frame of reference, the velocity of our frame of reference. Okay. So we will work out an example so you all can kind of see this in real time. So I'm going to zoom out a little bit. So let's say that we are in a swimming pool and we've got two lap swimmers swimming in two different directions here. So we've got Alyssa, who's swimming at a rate of 3 meters per second to the right side of the pool, while Mark swims at a rate of 4 meters per second to the left side of the pool. The question asks, what is Alyssa's relative velocity from Mark's perspective? Okay, so we are looking at Alyssa's velocity from Mark's perspective. So I'm going to put a little star by Mark. This is going to be our frame of reference here. Again, anytime that you all are working with something with direction, so in this case, we are working with velocity, which is a vector. I want you to imagine that there is a number line here, and we've got 0 obviously in the middle of our number line. Anytime an object is moving to the right, I want you to indicate that that object is positive. It's moving in the positive direction because those are toward the positive numbers on that number line. Anytime an object is moving to the left, I want you to indicate that with a negative sign, indicating that you are moving to the left toward the negative domain on the number line. So 2 quick changes I'm going to make in this problem really quickly. I'm going to indicate the direction. Our picture is already drawn for me, but I'm just going to add this extra step here right now. So you will see how this plays out momentarily. Okay, so we've got our picture. That is step number 1 when we are solving physics word problems. Step number 2, let's make a T-chart of what we know and what we don't know. I'm going to just write IDK for short for I don't know. All right, so let's look back at our problem here. All right, so we have Alyssa swimming at a rate of 3 meters per second to the right. So rate, anytime you see the word rate, I want you to be thinking velocity. All right, so I'm going to write VA for Alyssa, okay? Actually, so as not to confuse you, well, we'll say VA for Alyssa. Okay, so VA for Alyssa is going to be positive 3 meters per second. We do know Alyssa's velocity is 3 meters per second. And if you're confused about where I got that, that is right here in the problem. And it's also on the picture. Okay, going back to the problem. We also know that Mark swims at a rate of 4 meters per second to the left side of the pool. Now, since Mark is moving to the left, I'm going to be thinking that I should be putting a negative sign there. So again, negative 4 meters per second. All right, looking back at this equation, all right, so we've got VA. This is Alyssa's velocity, and we've got Mark's velocity. We want to know what Alyssa's relative velocity is according to Mark. So Mark is our frame of reference. So we are going to let, according to this equation, VB is going to be our frame of reference. So VB is Mark's velocity, and VB is also going to be our frame of reference. So what we are solving for here is VAB. In other words, what is Alyssa's velocity according to Mark? And I'm put parentheses, Mark's velocity is VB. Okay. Oops, I totally did not mean to do that. All right, so now that we've got that, we've got step number 2. Let's write out our equation. Our step number 3 is form our equation. So I'm going to write VAB equals VA minus VB. Now let's just plug these things in. So we don't know what VA is, so we're going on to step number 4. I'm going to leave VAB as is. We do know what VA is. So we know that VA is equal to positive 3 meters per second. Again, I'm leaving all my operations the same here. VA is Alyssa's actual velocity, right? We also know what VB is. So I'm going to plug in negative 4 for VB. That's Mark's velocity. All right, and now I am good to solve. So I'm going to add positive 3. Excuse me, I'm going to subtract negative 4 from positive 3. Now, again, anytime you have a minus sign and a negative number, I want you to just pretend that those are 2 plus signs. So now it looks like we are adding 3 and 4 together to get our relative velocity of 7 meters per second. So what this problem is really saying is even though Alyssa is only moving at a rate of 3 meters per second to the right, according to Mark, who is moving to the left, Alyssa actually looks like she is moving at a rate of 7 meters per second. Since they're moving in opposite directions, Alyssa looks like she's moving a lot faster than she actually is. So that is kind of the idea behind relative velocity there. All right, last thing we will go over is acceleration. So what is acceleration? How do we calculate it? Well, acceleration is the change in an object's velocity over time. Now, this might sound familiar because we've talked about what velocity is, and velocity is the change in an object's position over time. So what acceleration is saying is that velocity is now changing, right? So as a result of an object having velocity from its position changing, acceleration is now saying an object has acceleration because its velocity is changing over time. Now, acceleration, note, is also a vector. The variable we use to represent acceleration is the lowercase a. And our equation for solving for acceleration is A is equal to VF minus VI over T. So again, we are using, I'm going to zoom in a little bit here. We are looking at final versus initial again. So VF being the final velocity. And VI is our initial velocity. So this should look pretty similar to our equation to solving for velocity, only this time we are solving for acceleration. So anytime we are looking for the difference in two values, right? The final value minus the initial value, we are actually looking at the change in those values. So what acceleration really is saying is it's looking at the change in velocity. Remember, our delta sign means change in velocity over time. So let's look at what that might look like on our position versus time graph versus our velocity versus time graph. Because yes, with acceleration, we can actually have a velocity versus time graph. All right, so we have learned that the slope of this line on a position versus time graph. So we are looking at a position versus time graph here. Position's on the y-axis and time is on the x-axis. Our slope of the line here, all right, our slope. So, oops, and I'm doing that in the wrong color here. So our slope, our rise over our run, that is what our velocity is, all right? Acceleration. Now, acceleration is the change in velocity over time. So we are not going to have a standard, nice, pretty, linear slope for acceleration on a position versus time graph. It's going to curve upward or downward dependent on how an object's velocity is changing. However, on a velocity versus time graph, we do have a nice straight line. So the slope of a line on a velocity versus time graph. So notice now we have velocity on our y-axis and time on our x-axis. Our slope is in fact the acceleration of that object. So let's do a very quick example of how we might calculate an object's acceleration. Let's zoom in here. All right, so here we have this example of a car stopped at a red light, accelerates to a velocity of positive 10 meters per second in the span of 2 seconds when the light turns green. question is asking, what is the car's acceleration? So again, first step in any physics problem, I'm going to draw a picture. So rather than drawing out a car, I'm just going to make that car a dot. I'm going to indicate that it is accelerating. So, well, we do know we are solving for the acceleration, right? The car is stopped at a red light, right? So I'm going to write that it gives us an indication for what our initial velocity is, and that is 0 meters per second. And we know that it accelerates to a velocity of 10 meters per second. So I'm going to write my final velocity of this car is positive 10 meters per second. Anytime you see that positive sign, we should be thinking it is moving to the right. All right. We also know that our time is equal to 2 seconds. So what this is saying is that it is reaching a final velocity of 10 meters per second from stopped in a time of 2 seconds. All right. So really quickly, let's make a table of what we know and what we don't know. I'm just going to write IDK for short. All right, so we know if it stopped at first, our initial velocity, so VI is equal to 0 meters per second. We also know that it accelerates to a final velocity of 10 meters per second. So I'm going to write my final velocity is equal to 10 meters per second. And we know that it is over the span of 2 seconds. So I'm going to write that 2 seconds is our unit for time. So I'm going to write T is equal to 2 seconds. So we know our final, our initial, and our time. So what we are solving for is obviously our acceleration. All right, so now we've got our 2 steps. Let's go ahead and do step number 3, which is setting up our equation. Our equation for acceleration is VF minus VI over T. All right, double check that equation and it looks like we are good to go. Acceleration is by itself on its own side of the equal sign. So I'm ready to start plugging some things in. I'm going to leave acceleration as is. Again, leaving all of the operations, subtraction and division in this equation the same. I'm just plugging in numbers here. So what I've got for VF, right? So VF, we already indicated here on this T chart, is equal to positive 10 meters per second, right? We know that VI is equal to 0 meters per second. It started off in a stopped position. All right, and finally, we can plug in time. So we've got time over here in our T chart. Our time is equal to 2 seconds. We can go ahead and solve this problem, all right? Again, I'm just going to draw those parentheses here following the correct order of operations. So we've got 10 minus 2, or excuse me, 10 minus 0 is 10. Carry that 2 down, all right? So now we've got 10 divided by 2, and that is equal to, just keep those positive signs, positive 5 meters per second squared. So meters per second squared is going to be our unit of measurement for acceleration. All right, so I know that was a long video and we went over a lot, but go ahead and take some time to write a 1 to 2 sentence summary about what you learned on relative velocity, acceleration, and frames of reference. And I look forward to discussing this with you all in class.